Hey, this is Presh Talwalkar. How many of these mind-bending logic puzzles can you solve? Puzzle 1. This appears online with the saying that only a genius can beat it. We have several points, and we need to connect them by lines. But there are the normal rules. You have to connect the dots without lifting your pen and without going over any line more than once. How can you do it? So this is actually a classic mathematical problem. The challenge you're trying to do is to create a path that goes through every edge exactly once, but vertices can be revisited. This is what's known as an Eulerian path, and there is a mathematical result that can help you with this puzzle. You want to count the number of edges from each vertex. That's known as the degree of the vertex. You need all the vertices to have an even degree, or two vertices to have an odd degree. So let's just go ahead and count. Starting with this vertex, we can see that there are exactly two edges that come out from it. We then go to the next point, and we see there are two edges coming out from this. So let's just go ahead. This one has exactly two lines that are coming out from it. When we go here, we see there are going to be four different edges that come out of this vertex. So far, we have all even degree vertices. Now this vertex will have exactly three edges coming out from it. And that's the same for this vertex. We will have exactly three edges coming out from it. Let's just continue the count. This vertex will have two edges coming out from it. Then this vertex will have two edges coming out from it. And finally, this vertex will have two edges coming out from it. So what is the hint mathematically? We have exactly two vertices that have an odd degree. So you want to start your path from one of these two vertices. Once you know the starting point, this puzzle is relatively easy to solve. Let's start out with this leftmost vertex. Here's one way that you can connect all of the points without going over any edge more than once. Congratulations, we figured it out. Here is another solution that starts with the other vertex of odd degree. We have figured out another way to connect all of the lines without going over any line more than once. So now you are a genius. Puzzle 2. We have 5 people in a room. Every single person is either a truth teller who always tells the truth or a liar who always lies. Each person knows the type of everyone else. You ask each person, how many liars are among you? And the 5 people give the following responses. They give the answers of 1, 2, 3, 4, and 5. The puzzle is, how many liars are in the room? Let's work through it logically. So let's suppose there was just one liar in the room. So suppose this person was a liar. Then the other 4 people would all be truth tellers. So all of the truth tellers, which are 4 of them, there would be 4 truth tellers that would give the answer of 1. But we know that in this puzzle, that was not the case. So it's not possible that there was just one liar. Similarly, what would happen if there were 2 liars? Say these were the liars. Then the other 3 people would be truth tellers, and each of those 3 truth tellers would say the answer of 2. But this didn't happen in the puzzle either, so we know this cannot be the case. If there were 3 liars, then the remaining 2 truth tellers would say that there are 3 liars, so we'd get 2 answers of 3. This didn't happen, so we know that's not the case. If there were 4 liars, then we would have 1 truth teller who gives the answer of 4, and that's exactly what happened in the story. So we know that there are 4 liars, but let's just see what would happen if there were 5 liars. Then every single person would have to tell a lie. So no one could possibly give the answer of 5 because that would be the truth. This didn't happen because one person did give the answer of 5, so we know there cannot be 5 liars. So the only possibility that matches the story is that there are exactly 4 liars. The one person who gave the answer of 4 must be a truth teller. So there are 4 liars in the room. Puzzle 3. There are 50 people standing in a line. and each person is looking at everyone in front of them. Let's just number these people. Starting from the very end, the person is numbered 50, and then we decrease this until we get to person 1, who is looking at no one. Each person is either a truth teller, who always tells the truth, or a liar, who always lies. Each person knows the type of everyone else. The person at the very back, numbered 50, says everyone in front of me is a liar. Person 49 says everyone behind me is a liar. Person 48 says everyone in front of me is a liar. And person 47 says everyone behind me is a liar. This pattern continues all the way alternating until person 2 says everyone in front of me is a liar and person 1 says everyone behind me is a liar. The puzzle is, at most, how many people can be truth tellers and who are the truthful? This problem appeared in the Bangladesh Mathematical Olympiad. So let's work through it logically. Let's start by considering if the very last person, person 50, was a truth teller. Person 50 says everyone in front of me is a liar. So if this is a true statement, then every other person has to be a liar. But now let's examine the statement of number 2. Number 2 says everyone in front of me is a liar, and we know that person 1 would be a liar, but that would make this a true statement. This is a contradiction to the fact that person 2 has to be a liar type. So this cannot possibly be true. We cannot have person 50 be a truth teller. So person 50 must be a liar. Now what about person 49, who says everyone behind me is a liar? We know that person 50 must be a liar, so this is a true statement, and person 49 must be a truth teller. Let's advance to person 48. Everyone in front of me is a liar. If this person were a truth teller, then everyone in front of this person would be a liar. But now once again, person 2 says everyone in front of me is a liar. We know that person 1 is a liar by this implication. So this is a true statement, and once again we have a contradiction to the type that person 2 is a liar. So we cannot possibly have person 48 be a truth teller. So person 48 must be a liar. Now by similar logic, persons 46, 44, all the way to person 4 must be liars, or else person 2 would be a liar that is saying a true statement. So we know all the even people from 46 to 4 would be liars. Now let's examine person 47. Everyone behind me is a liar. We know that person 49 is a truth teller, so this cannot be a true statement, so person 47 must be a liar. Similarly, persons 45, 43, 41, all the way to person 1, all of these odd numbered people must be liars because we know that person 49 has to be a truth teller. So we have all of these odd numbers are liars. We know that person 1 is a liar. So now we know that everyone from 46 to 3 is a liar. So all of these dots will be liars. So all we need to do is examine person 2 now. Everyone in front of me is a liar. We know that person 1 is a liar. So this is a true statement. So person 2 must be a truth teller. So we've now figured out the type of every single person. We know there must be 2 truth tellers, persons 49 and 2. And that's the answer. Puzzle 4. This is a unique matchstick puzzle. We have a fraction. 7 over 9 is equal to 3. The challenge is to move 2 sticks to make a true equation. I credit Matchstick Puzzles Blogspot for this puzzle. So how can we figure this out? So let's think about fractions we can make. 9 over 3 is equal to 3, 3 over 1 is equal to 3, 0 over 7 is equal to 0. But considering the numbers we can make from the matchsticks, I couldn't figure out any way to move just 2 matchsticks to make any of these fractions true. So we have to think creatively. The amazing solution is that 1 over 3 is equal to 3 to the power of negative 1. So let's see how we can work this out. We need to change the 7 into a 1. So we will take this matchstick and make it the negative of the exponent. And now we need to make this 9 into a 3. So we take this matchstick and we make it as 1. So we now have a true equation. 1 over 3 is equal to 3 to the power of negative 1. What an interesting matchstick puzzle. Puzzle 5. We have a right triangle ABC where AB is equal to BC is equal to 6. Construct midpoints D along AB, E along BC, and F along AC. Then construct a square and construct a right triangle DBE. Repeat this process in the triangle FEC. We make midpoints, we make a square, and then we construct another right triangle. We will continue this process and shade these triangles and continue it indefinitely. The question is, what area will be shaded by all of these blue triangles? A version of this problem was asked on the AMC in the year 1999. This is one of the qualifying tests for the Mathematical Olympiad in America, and 80% of the students actually missed this problem. So it's a pretty interesting question that was challenging to many students. So how can we figure it out? There are definitely many different solutions, but I'm just going to present two that I find interesting. So let's start out with this entire isosceles right triangle. We know its area will be 1/2 its base times its height. Its base and its height are each equal to 6, so the area is 1/2 times 6, which equals 18. So let's go to the first step of the construction. So what can we say from the very first step? What can we say about this right triangle? Well, let's consider the trapezoid ABEF. If you look at this shaded triangle, you'll actually see two other identical or congruent triangles. So here we have a congruent triangle, and here we have another congruent triangle. So this trapezoid is made up of 3 of these congruent right triangles. So the area that's shaded is exactly 1/3 of this trapezoid. Now let's go to the next trapezoid constructed in the next step. Once again, we see that the shaded triangle will be 1/3 of the area because there will be 2 other congruent triangles. And in fact, this process will continue indefinitely. The shaded triangle will be 1/3 of its respective trapezoid. So in the end, we can see that all of the shaded triangles will end up being 1/3 of the total area because all of the trapezoids together make up the entire triangle ABC. And we know that every single trapezoid is shaded by 1/3 of its area. So the shaded area will be 1/3 of the entire triangle ABC's area. So this will be 1/3 of 18, which is equal to 6. And that's it. Now let me show another way to look at this area in terms of infinite series. We can consider this first triangle, and we can see that it will be 1/4 of the entire triangle ABC. So this shaded triangle will be 1/4 of the entire triangle's area. Now, when we get rid of this trapezoid, we have gotten rid of 3/4 of the area, so only 1/4 is remaining. Once again, in this area, this shaded triangle will make up 1/4 of the remaining 1/4 of the triangle. So this shaded triangle will be 1/4 of 1/4 of the whole triangle ABC. So this will be 1/16 of the entire area of ABC. And this process will continue indefinitely. Here we now have 1/4 of that triangle. So that will be 1/4 of 1/4 of 1/4 of the whole. So we will end up with an infinite series where each time we're dividing by 4. We can now factor out the area of triangle ABC, and we get the infinite series 1/4 plus 1/4 squared, and so on. And we all know that the sum of this geometric series will be equal to 1 over 3. So once again, we end up with 1/3 of the entire triangle's area. 1 over 3 times 18 is equal to 6. And that's another way to solve this problem. Puzzle 6. A father has 49 gold coins. The first coin weighs 1 gram, the second coin weighs 2 grams, and so on, with the 49th coin weighing 49 grams. He wants to give 7 coins to each of 7 sons so that every son gets coins of the same total weight. Can you find a way to distribute the coins? I thank Subash for the suggestion. So here's how I approach the problem. We start out that we have coins weighing 1, 2, 3, all the way up to 49 grams. So what's the total weight of all of the coins? We have the sum of the numbers going from 1 to n, where n is equal to 49. So we substitute into the formula n times n plus 1 all over 2, where n is equal to 49. And this simplifies that the total weight is equal to 1,225. So we need each of the 7 sons to get an equal amount. So each son needs 1225 divided by 7, which equals 175 grams. But how can we partition these numbers into 7 sets with an equal sum of 175? I admit I actually got stumped at this point, and I did a search. And I found out with a truly remarkable solution. We can actually use something that's been solved since ancient times. Use a 7 by 7 magic square. This is actually a sufficient condition because you will even have the diagonals have the same sum of 175. How many 7 by 7 magic squares are there? There are so many, we don't know the actual number, but it's over 3 decillion. So there are many, many solutions to this puzzle. But I just want to illustrate a couple of ways that you can construct a 7 by 7 magic square. So one of the methods that's been known since ancient times in China was the Lo Shu method. This will generate magic squares of odd order. So let me illustrate the method for 3 by 3. So we first write the numbers 1, 2, 3 vertically. To the left, write 4, 5, 6, and to the left, write 7, 8, and 9. Now comes the magic. Rotate this counterclockwise by 45 degrees. So now visualize a 3 by 3 magic square made out of 9 numbers. We just need to fill in the gaps with 4 numbers. So we are going to take each number that's outside of the square and fill it on the opposite row or opposite column. So here this 1 is going to travel all the way to the bottom. Then this 9 is going to travel all the way to the top. The 3 will travel to the left side. And this 7 will travel to the right side. And voila! We have a 3 by 3 magic square. Every single row will have exactly the same sum of 15. Every single column will have the same sum of 15. And the 2 diagonals will also have the same sum of 15, but we don't need that in this particular problem. But now we need to construct a 7 by 7 grid like this. So we start out by writing the numbers 1 through 7 vertically. To the left, write the numbers 8 through 14, and we will continue writing these numbers until we create a 7 by 7 grid. So we write the numbers going all the way up to 49. So we now use the Lo Shu technique. We're going to rotate this entire grid 45 degrees counterclockwise. Now, let's visualize a 7 by 7 grid like this, and we will apply the same technique. We will fill in the gaps with the things outside of this square, and they need to travel to the opposite side. So here we have a triangular array of numbers, and it needs to travel to the opposite side. So we're going to fill in the missing gaps over here. So let me just color these numbers and let them travel to the opposite side. We will do the same thing on the bottom. This triangular array will fill in the gaps on the opposite side, so we will fill in the gaps right over here. On the right side, we have a triangular array, which will travel to the left side of this magic square, and the final numbers will fill in the right side. And amazingly, we have created a 7 by 7 magic square. So every single row will have exactly the same magic sum of 175, and every single column will have exactly the same sum of 175. So you could distribute the coins according to the 7 rows. You could distribute the coins according to the 7 columns. And these are amazing solutions. It's truly remarkable that they figured out these patterns in ancient times before they had any modern calculators or computers. But this is not the only method that the ancients figured out. Here's another method that's been known as the Siamese method for odd-ordered magic squares, and it originated in the city of Surat in India. So imagine we have a 7 by 7 grid. In the very top row, in the middle, write the number 1. Now create an auxiliary row above it, and imagine this is actually going to wrap around to the bottom row of squares. Create an auxiliary column to the right, and this is going to wrap around to the first column on the left. In the upper right, we're going to create one special square, which is just an occupied square. So we're going to treat it as if it already has a number written in it. Here's the remarkable method. We will just write numbers diagonally up to the right. So we have the number 1, and we're going to write the number 2 here. But we're already outside of our 7 by 7 grid, so it's going to wrap around from the very top. We're going to wrap around to the bottom. So we write the number 2 here. We now continue going diagonally up to the right. So we go 3, we go 4. Now we go diagonally to the right. We're off the grid. So this number 5 will actually wrap around to the left column. So we're going to put a 5 here. We go diagonally to the right, we write 6, then we write 7. Now we have an occupied square. So when you run into that trouble, you just go down. So we write the number 8 here. So now we go diagonal to 9 and 10. Now we're off the board, so we're going to go back to the bottom. So this is going to be 11. So we go diagonal 12, diagonal 13, but we've wrapped around. So this is going to be 13 in the left column. Here we have 14. Now we've hit an occupied square, so we're going to go down to 15. We diagonally go 16, 17, 18, 19. Now we're off the board, so we need to go down to the bottom row, and this will be 20. We go diagonally, we're off the board, so we go 21 here. Now this will be occupied, so we just go down to 22. And we continue diagonally 24, 25, 26, 27, and 28. Now comes a special case. We go diagonally off the board, and this square is just occupied. So we don't wrap around, we just treat it as an occupied square, and we go down. So here we have 29. We now go diagonally, we're off the board, so we wrap around to the beginning, and this will be 30. And the rest of the square I will just tediously fill in, and we can fill in all 49 of these magic squares. It makes you think, how did they think of such a remarkable pattern in ancient times, and how did they prove this work? It's quite an amazing process that they were able to do such calculations. We wrap around to the bottom, and now we just need to figure out the remaining cells. We're almost done. Occupied here, so we have 43, 44, 45, one more wraparound, 46, 47, just 2 more cells remaining, and finally we wrap around to 49. And voila, we have created a 7 by 7 magic square, and every single row has exactly the same sum of 175, and every column has the same sum of 175. The diagonals will also have this same sum. What a truly remarkable solution. And I'll just mention, we started with 1 in the middle of the first row, but you can actually start with 1 anywhere. You just may not get the diagonals to have the same sum, but you would definitely have all of the rows and all of the columns have the same sum, so you would be able to generate other solutions. You can distribute the coins according to the 7 suns as 7 rows or the 7 suns as 7 columns. What a truly magical solution to this problem. Thanks for making us one of the best communities on YouTube. See you next episode of Mind Your Decisions, where we solve the world's problems, one video at a time.